All right, so continuing from last week we talked about this convolution property. Okay, so convolution property is especially important for analyzing linear time invariant systems, because we know that when we pass a signal, let's say x of t, through a linear time invariant system with the impulse response h of t, then the output is the convolution between the input and the impulse response. So with the convolution property, we now know that the spectrum of the output will be equal to the product of the Fourier transform of the input times the Fourier transform of the impulse response, which we call the frequency response. Okay? Now this relationship is favorable because computing a multiplication is usually much easier than computing the convolution. Okay, and we will see a few examples in a moment. Okay. All right. So what we know from last week's discussion, right? First of all, is this convolution property, and second of all, we sort of identified the fact that the frequency response that we learned earlier is actually just the Fourier transform of the impulse response h of t. Okay. Now, since the Fourier transform pair is unique, therefore, if you say that you can completely characterize the system by the impulse response, then this means that you can also characterize the system by its frequency response. Okay. So given one or the other, right, is sufficient to characterize a linear time invariant system. Okay. All right. So this is what I just mentioned, right? Since a linear time invariant system is completely characterized by h of t, it is also characterized by its frequency response. Now, because of this, right, there are several properties that you can more easily show in the frequency domain compared to the time domain. Okay. So this property for the cascade of two linear time invariant systems is one of these examples. So previously, we showed using the convolution that when you cascade two linear time invariant systems together, the effective input and output relation is not impacted by the order of these two for which you cascade these two systems. Okay, so this is saying that if you have x of t first pass through a system h1 of t, and then through a system h2 of t to get y of t, this is equivalent to passing x of t first through h2 and then through h1. Okay? Okay. So previously, using the relationship of this convolution, right, we showed that when you cascade two linear time invariant systems, it doesn't matter what order you place the two filters, the two systems. Okay. Now, with this convolution property, we can show the same thing using multiplication, right, which is much simpler. Okay. So now, suppose that you pass a system x of t, right, first through the system h1, right, assuming having a frequency response capital H sub 1, and then through a second system with frequency response capital H sub 2 to get y of t. Then suppose that the frequency response of x of t is xj omega. Okay? So then when you pass through the first system, you will get an output that is equal to h1 j omega times xj omega. And if you further pass this through a second system, then the output yj omega is just h2 j omega times h1 j omega times x j omega. Okay? Now, if you view h1, h2, right, if you view the multiplication of h1 and h2 as one effective frequency response, then this is like passing x of t through a single linear time invariant system with a frequency response that is equal to the product of the two. Okay? Now, due to the commutative property of the multiplication, h2 times h1 is equal to h1 times h2. And therefore, this is also equal to passing x of t first through a system with frequency response h2, and then through a system with frequency response h1. Okay? So this property that we previously showed using the convolution is now more easily showed using this multiplication of the frequency response. Okay? So this is just one example to show how proving properties in the frequency domain using this multiplication can be much easier than doing this in the time domain using the convolution. Okay? Now, one thing you should note is that, actually not all systems may have a frequency response. Okay? So the frequency response is the Fourier transform of the impulse response. But not all impulse responses h of t have a valid Fourier transform. Okay? So for a system to have a frequency response, this means that the Fourier transform must exist for h of t, meaning that it should satisfy the Dirichlet condition, which it has three conditions. Right? One is that it should be absolutely integrable. The second is that it has to have finite extreme points. And the third is to have finite discontinuities. Okay? Now, the second and third ones are much easily satisfied in practical systems. Right? So most practical systems would not have these extreme cases where you have infinite extreme values or infinite discontinuities. Okay? But a practical system could have a response that is not absolutely integrable. Okay. But this also is not a problem if you are looking at stable systems, because you can show that if a system is stable, then its impulse response must be absolutely integrable. Okay. So often the key to whether or not the frequency response exists is whether or not h of t is stable. Okay? Because you can show that if h of t is stable, then it is absolutely integrable. Okay? All right. So you can try to show this using this bounded input, bounded output stability definition by yourself. Okay? All right. Now let's look at a few examples. So in this first example, we consider a continuous linear time invariant system with impulse response h of t equal to delta of t minus t naught. Okay. Now suppose you pass a signal x of t through this system. So for input x of t, the output is y of t equal to h of t convolved with x of t. Okay? Now, when you convolve x of t with the delta function at time t0, this basically shifts the signal to time t0. Okay. So this system, if it essentially performs a time shift on the input signal. Okay. Now let's look at this from a frequency domain. All right. So suppose that x of t has a Fourier transform that is capital X of j omega. Okay? Then the Fourier transform of y of t, of the output y of t, is this y j omega equal to h j omega times x j omega. Okay? So this is due to the convolution property. All right. Now, what is h of j omega? All right, so we obtained this by taking the Fourier transform of this delta function at time t0, okay? And that will give us a complex exponential, minus e to the minus j omega t naught, okay, times x of j omega. All right? So if you compare the two, this is saying that x of t minus t naught has a Fourier transform that is equal to x of j omega times a phase shift that is e to the minus j omega t naught. Okay? And this is exactly the time shifting property that we showed before. Okay? So this is the time-shifting property of the Fourier transform that we showed before. Okay. Okay. Now, for the second example here, we're looking at an output that is equal to the derivative of the input. Okay. So this is a linear time-invariant system that we call a differentiator. Okay. Now, suppose you're asked to find the frequency response to this linear time-invariant system. So you can do this, right, by first employing the differentiation property. Okay, the differentiation property of the Fourier transform, which shows that when you take the derivative of x of t, its Fourier transform will be x of j omega. Right, its Fourier transform will be the Fourier transform of x times j omega. Okay? Now, by the fact that y should be equal to the frequency response times the Fourier transform of the input, therefore, you can imply that this j omega is the frequency response of the system. Okay? So this, hence, the frequency response of a differentiator is this j omega. Now, another example. Okay. So here we have the example of an integrator. Okay. So we know that for this system, the impulse response is h of t equal to u of t, okay? Because the integration of x of t from minus infinity to t can be written as the convolution of x of t and the unit step function, okay? Now, previously, in the previous example, we showed how to take the Fourier transform of a unit step function, okay? So by taking the Fourier transform, we have the frequency response. So this is by example 4.11, okay? We showed that the Fourier transform of h of t, which is the frequency response, is 1 over j omega plus pi delta omega. Okay? So with this frequency response, you can then find what is the Fourier transform of y. So then the Fourier transform of the output y of t is y of j omega equal to h j omega x of j omega. Okay. All right. And then we just plug h inside here, and we will get 1 over j omega xj omega plus pi x0 delta omega. Okay? And this implies that this should be the Fourier transform of this, right? Which is consistent with what we learned before. Right, so this is the integration property. Okay. Now, knowing that the impulse response and the frequency response has this Fourier transform relationship, it also allows us to analyze the system from both a frequency domain perspective and also a time domain perspective. Okay. So previously, we looked at this ideal low-pass filter as an example of an ideal frequency selective filter. Okay. So for this ideal low-pass filter, our goal is to let through signals that have a bandwidth lying between minus omega c to omega c, and cut everything off, beyond that. Okay. Now, if you take the inverse Fourier transform of this, then you can find that the impulse response h of t takes on this sinc function form. Okay? And this is plotted below. Right? So this sort of allows you to look at what happens both from the frequency domain and in the time domain. Okay. So from this example here, you can sort of see the trade-off that we may have when designing such a filter. Okay. So when we're designing a low-pass filter, ideally, we hope to let through signals within a frequency band perfectly with gain 1 and perfectly shut out everything beyond that. Okay. But what you sacrifice by using this ideal filter is that in the time domain, you get something that looks like this. Okay. So this thing is not ideal in several different ways. First of all, this impulse response has non-zero values extending to minus infinity. Okay? So this means that this filter is non-causal, okay, and actually extends to minus infinity. And secondly, this signal is very difficult to realize perfectly using a simple circuit. And furthermore, it has these large ripples that are not desirable. It may cause some undesired oscillation at the output. Okay? So even though in the frequency domain, it provides an ideal response, right, by letting through signals that we want and perfectly eliminating those beyond a certain frequency, but in the time domain, it has several non-ideal properties. Okay? So this is listed here. Using this ideal low-pass filter, right, we have to deal with this, the fact that it is non-causal, not easily approximated, and that it has this oscillatory behavior. Okay? So in practice, you never really use this ideal low-pass filter. Right? You have to use something simpler, right, to replace it. Okay. So for example, you could have instead used a filter with impulse response that looks something like this. Right? So this is very simple. This is just a single-sided decaying exponential. And in fact, you can implement this using a simple RC circuit. Right? So this filter here is, first of all, simple to implement. It is causal. Right? It is causal because it is 0 in a negative domain. Okay. And that it is non-oscillatory. Okay? So its response doesn't really, oscillate. Okay? And in fact, decays monotonically. Okay? But having these ideal properties in the time domain, right, requires you to sacrifice something in the frequency domain. Okay? So in fact, if you take the Fourier transform of this to get its frequency response, you will see that its response, right, at least the magnitude of the response, looks something like this. Okay? So if you compare it to an ideal low-pass filter, right, you can see that it does really bad because it does not really eliminate any frequency beyond something that you desire, right? It just tries to sort of suppress it, but it cannot really perfectly eliminate them. All right, so this filter, even though simple, has bad frequency selectivity. Okay, so this is sort of just a side note to using this example to show you some considerations that you may have when designing filters. Okay, so you may learn more about this in a course on, let's say, communication system or some circuit design class. Okay, so in practice, you can never really implement this ideal filter, but you also don't really use something so bad, right? You try to trade off between these two. Okay. Now, suppose that we do consider a filter like this,